Hi, Doc Revis here. In this video, I will show you how to work some simple calorimetry problems. Let's start by examining two formulas that are used in carrying out calorimetry problems. One formula we use when we have constant pressure. Q, heat, equals mass times specific heat times delta T, with delta T being T final minus T initial. The other formula we use for constant volume. That formula would be Q calorimeter equals the heat capacity of the calorimeter times delta T. Again, with delta T equal to T final minus T initial. So these are the formulas and the units used for each of the variables. Let's work a problem involving constant pressure. Here it is. A bar of lead having a mass of 26.47 grams at 89.98 degrees C was placed in a constant pressure calorimeter containing 100 mils of water. The water temperature increased from 25.50 degrees C to 23.17 degrees C. What is the specific heat of the bar of lead? Since this is a constant pressure calorimeter problem, we will use Q equals ms delta T. Another way to know to use this particular formula is typically when we transfer a hot metal to a water solution, this will be the formula to consider. It's important to note that we have all the values for this except the mass. However, we do have the volume, 100 mils of water. Therefore, a quick conversion would take 100 mils of water to 100 grams of water. So let's proceed with working this problem. Based on the laws of conservation of energy, we know that lead heat plus water heat must equal 0. Therefore, Q water equals minus Q lead, or Q lead equals minus Q water. Therefore, if we solve for water, the heat value for lead will have the same value with the opposite sign. Therefore, we take the equation, we plug in the mass, the specific heat for water at 4.184 joule per gram degrees C, times delta T, 23.17 degrees C minus 22.50 degrees C. We solve this through and we obtain 280.3 joules of heat for water. Therefore, the heat for lead must equal minus 280.3 joules. So, since the heat lost by the lead bar equals the heat gained by water, we set lead equal to minus 280.3 joules, and we use it to solve for the unknown specific heat, which we've designated as S. We take the equation, Q equals ms delta T. We plug in the values, the heat of lead minus 280.3 joules equal to the mass of 26.47 grams, the unknown specific heat times delta T. We rearrange the equation and we obtain specific heat of 0.158 joules per gram degrees C for this constant pressure calorimetry problem. Next, let's carry out a problem involving constant volume. And here's the problem. A sample of 1.435 grams of naphthalene was burned in a constant volume calorimeter. The temperature of the water increased from 20.28 degrees C to 25.95 degrees C. What is the heat of combustion of the device plus water with a heat capacity of 10.17 kilojoules per degree C? carry out this problem, we set up the equation, Q equals C delta T, and we simply plug in each of the values, 10.17 kilojoules per degree C for the heat capacity, times delta T, and we obtain 57.66 kilojoules. Note that this is the heat of the calorimeter. Therefore, the heat of the reaction will have the opposite sign. So the calorimeter had positive 57.66 kilojoules. Therefore, the heat of reaction will be minus 57.66 kilojoules. That is the heat for this process. In many cases, you will want to obtain the heat per mole of the substance. Therefore, the question would read, what is the molar heat of combustion? To do this, it is a straightforward dimensional analysis where we convert the grams of naphthalene into moles of naphthalene using the molar mass of naphthalene. When we do this and divide the minus 57.66 kilojoules by the moles, we obtain 5,185 kilojoules per mole. Note that in this problem that we do not use the mass unless we're looking for heat per mole. So there you have it, how to work calorimeter problems involving constant pressure and constant volume.